Part C, general purpose registers and addressing modes. We learn two topics in this part. Part C.1, general purpose registers. All right. First, so let's look at this concept, general purpose registers. Yeah. Reasons for using general purpose registers. We use GPR to refer to this special type of general purpose registers. Yeah. Later, we have another type. Yeah. FPR, floating point registers. FPR, floating point registers. Floating point operation, general purpose register, we use this registers to do integer operations. Integer operations. Then the floating point, we use FPRs. Yeah. All right. First, registers like other forms storage, that means stack, accumulator, right? Yeah, are faster than memory. So that here, it means if you get data from registers, it is much faster than you get data from memory. Yeah. All right. Second, registers are more efficient for compiler to use than other forms of internal storage. Here we talk about stack and accumulator. Yeah, AC. Okay, yeah, stack and AC. Yeah. Compiler. Yeah, compiler likes registers. Yeah, actually, compiler can do a lot of things using registers. We know there are relatively large number of registers. When we use registers, there are, for GPR, there are 32, right? I mentioned last time. FPR, another 32. Yeah. So the compiler needs to arrange these number of registers as the resources, because registers are precious resources to be used in program execution. Yeah. So the compiler needs to find a good way to use these resources. Then the execution can be faster. Yeah. So that's a important topic. Later I can talk about a little bit. Yeah. All right. Order to evaluate an expression. When you are given arithmetic operation, expression, many times you have freedom to choose in what order to get the result, to find the result. Yeah. If you have freedom to do the operation to get a result, then you have chance to make your operation faster. If you do not have the freedom, then you may not be able to make the operation faster. Yeah. So that's the reason. Yeah. An expression may be evaluated in different orders when you use registers. Yeah. When you use registers, which may be more efficient. Yeah. To understand why when you use register that may be more efficient, you can change order of execution. You can change order of execution. To understand this point, we need more study. We need to study, several more topics so we can understand. Yeah. At this point, we do not have that background. It is a little harder to understand. Yeah. But later, after we understand instruction level parallelism, then we can understand this topic better. Yeah. All right. On a stack computer, the hardware must evaluate the expression in only one order. Yeah, stack. You do not have freedom. You have to use, pop, push. You have to use one single order to do the execution. So that restriction, does not help you take advantage of instruction level parallelism to make your execution as fast as possible. Okay, yeah. So why? Yeah, because we need more background to understand that. Here, just give you the answer first. Yeah. Next, using registers. Yeah. First, let's look at the memory traffic. I mentioned a little bit, more memory trips, right? Yeah, I talk about that. Yeah, more memory trips. So that's the memory traffic issue. Yeah. Using registers, the memory traffic reduces. Why? Because after we store the data in the registers, we can reuse them, right? We can reuse data stored in the registers. So that can save us many memory trips, reduce the memory traffic. All right, so the program speed up. As a result, the program speed up. Yeah. All right. The code density improves. Code density. Here you see code density improves. Since a register can be named with fewer bits than memory location. Yes. Yeah. In your instruction, when you need to get the data, you just use the register location, right? Register location, that 5 bits. You can avoid using memory location, long bits. In that way, your code density improves. Yep. You do the same thing, but your code, your instructions need fewer number of bits. That's the code density improved. Okay? Yeah. All right. How compiler use registers. Compilers. Yeah. Here. Yeah. So this is a compiler optimization topic. Compiler optimization topic here. Yeah. We know compiler, some advanced software, yeah, doing the translation from higher level language to machine language. Yeah. From the lower level instructions. Yeah. All right. But here, regarding the registers, compilers allocate registers to variables based on some algorithms to achieve more efficiency. So compiler plays a big role here. Yeah. How about the efficiency? Yeah. All right. There are many different ways to use the register resources, right? It's not the only way, right? There are a lot of freedom for the compiler to choose different ways to use the registers. You can use this way, you can use that way. Yeah. The performance will be different. Some way you need to use more registers. The more register you use, you waste more resource. Then the overall performance will be slower. Okay? Yeah. If you can find a faster way, optimal way to use your memory resource, then your performance will be faster. Yeah. But what is the optimal way? So that problem actually pretty hard to solve. Solving that problem, it corresponds to the graph coloring problem. The graph coloring problem. So I hope you know the graph coloring problem. It is a very difficult problem. NP complete. Okay? NP complete problem. Graph coloring problem. Very, very hard. Yeah. So the compiler optimization problem corresponds to the graph coloring problem. That means if you want to find optimal solution, it is very difficult. So usually the compiler just find a near optimal solution, not necessarily absolute optimal. Don't need. It's a near optimal. Yeah. So that's good enough. Yeah. So that's the, efficiency issue. Yeah. All right. Yeah. But for this class, I do not plan to talk that part a lot. Yeah. So that part pretty deep. Yeah. So I do not plan to go that far. Yeah. All right. Next. GPR architecture types. Yeah. So there are several factors, aspects when we talk about GPR architectures. Yeah. Whether an ALU instruction here, ALU again, so we mean arithmetic and arithmetic logic X and or, right? Not, yeah, logic operations unit, ALU unit. Some device called arithmetic logic unit. So you can do arithmetic operations. You can also do logic operations in that unit. So that's the ALU, yeah, instruction. Has 2 or 3 operands. Sometimes you use 2 operands, sometimes you use 3 operands, right? So remember, I use example like, R3, R1, B, we use this 3 operand example, right? You know the meaning, right? Okay. Another version, 2 operand version, R3 and B. I also use this as another example, right? Both you can do the same thing, addition, yeah. But this, the source, S1 here, S2, but this is destination, okay? Yeah. Here, S1 here, S2 here, source, 2 sources, but this also used as destination, yeah. So you know the difference, yeah. So here, instruction types, right? Architecture types, 2 or 3 operands you need in your ALU instruction. This is ALU instruction. Okay. All right. In a 3 operand format, the instruction contains 1 result operand. So this is a result operand. Okay. And the 2 source operands, they are separated. Okay. Separated. So result, source, they are separated. Yeah. In a 2 operand format, one of the operands is both source and a result. Here, this one, both source and a result for that operation. Yeah. Okay. Yeah. Another aspect, how many of the operands may be memory addresses in ALU instructions. ALU instructions, based on different architectures, sometimes you need some operands coming from memory. How many? Certain number of operands coming from memory. Yeah. So that number also could be different. Yeah. So the number of memory operands supported by a typical ALU instruction may vary from none to 3. See that difference? 0, so no operand for ALU. Okay, yeah. Load store, not ALU. Okay, yeah. Load operation, store operation, not ALU. Okay, yeah. So here, because here we're talking about ALU operations. For ALU operations, there is a 0 case. So that means ALU operations are not allowed to access memory. If you want to access memory, you can only use load or store operations. So that's the reason we use 0. Okay, 0 case. Then you have 1 case, only 1 operand can access memory. 2 case, 2 operands, up to 3. Yeah, that's the possibilities for, all the possible GPR architectures. Yeah. All right, so let us finish C.1 here.